So the correct answer would be A, which is Q equals 3.2 times 10 to the negative 20th coulombs. And why is A impossible? Why can't you have a charge of 3.2 times 10 to the negative 20th? Well, if you recall, charge always comes in packets. Q equals NE. So the trick is, all you do is just take Q here and you just divide it by the charge of an electron, which is 1.6 times 10 to the negative 19th. And 3.2 times 10 to the negative 20th is less than 1 electron. 6.4 times 10 to the negative 19th divided by 1.6 times 10 to the negative 19th is actually 4 electrons. 1.12 times 10 to the negative 18th coulombs, you could do that in your head. I wouldn't do that. Just divide that into a calculator. By 1.6 times 10 to the negative 19th is actually 7 electrons. And then finally, 4.8 times 10 to the negative 19th coulombs divided by the charge of an electron, 1.6 times 10 to the negative 19th is 3 electrons. So in other words, back to the donut analogy, you can go to Dunkin' Donuts and you can buy 3 donuts, 7 donuts, 4 donuts, but you can't buy 3/4 of a donut. At least not that I know of. Next, let's talk about Coulomb's law. Coulomb's law is named after Charles Coulomb, who in the late 1700s did a brilliant experiment to measure electrostatic forces using a special balance called the torsional balance here. And this is what he came up with, that the force of any 2 electrical charges is equal to the amount of charge present on each object, Q1, Q2, divided by the distance squared. And then to make this into equation, there's a constant of proportionality called the Coulomb's constant. So to break this down, F is the force of the electric charges measured in newtons. K is the Coulomb constant. That's a number he was able to measure. And you don't have to know how to derive this. We're just going to use it. It's 9 times 10 to the 9th. And then the units are weird because it's a constant of proportionality. Newton meters squared over Coulomb squared. It just makes this relationship into an equation, makes it work there. And notice the Coulomb constant is a very large number. 9 times 10 to the 9th is 9 billion. So the electric force is very strong relative to, say, like gravitational forces. Q1, Q2 is the amount of charge present on each object, measured in coulombs, named after Charles Coulomb. And then finally, D is the distance between the charges, measured in meters. And finally, if you get a negative answer, then it's a force of attraction. If you get a positive answer, it's a force of repulsion. And that's because if you have 2 positive charges or 2 negative charges, you're going to get a positive force. But if you have a positive and negative charge, you're going to get a negative force of attraction. So conceptually, what does Coulomb's law mean? It seems like a lot of weird math here. So let's try to break it down for you. So Coulomb's law is basically a way to put mathematical structure to what happens in nature. So what he basically figured out by doing a lot of experiments is that electric force can be measured by using his constant, which he eventually measured. But more importantly, conceptually, here's what's going on. It just depends on how much charge you have on each of your objects, and then it's inversely proportional to the distance squared. And by Newton's third law, the forces are always equal and opposite to each other. So practically speaking, how does this work in real life? From calculating the chances of lightning strikes to building semiconductors and electronics to doing simple static electricity experiments, Coulomb's law is at work here. So a classic thing is you take a balloon, which is a plasticky material, and you rub it on a fleecy, woolly material. Plastic things like to grab electrons, so we build up charge. Let's say on object 2, this is my balloon here. And as the plastic grabs more electrons, it has a negative charge because the fleecy, woolly object gives away charge, becomes positively charged. And then that can attract either the fleece or wool, or in this case, the can. And even though the can doesn't have a net charge, it'll still be attracted because it's polarized here. And all it is if I build up more charge on each of the objects, let's say I have 10 times as much charge on the balloon, well, there's going to be 10 times more electric force per Coulomb's law. And the other factor is the distance, the inverse of the distance squared. So if I move the balloon twice as close, it's not going to have twice the force. It's going to have 2 squared, which is 4 times the force. If I move it 5 times closer, it'll be 25 times the force. And then the inverse is true too. If I move it twice as far away, it's not twice as weak, it's 4 times weaker. And so if this looks a little deja vu, that's because a lot of things in nature obey the inverse square law. So for example, gravity is the same thing, where the gravitational force equation looks almost exactly the same, except it's not charges, it's masses of objects. It's the gravitational constant, which is a lot smaller, and it's inversely proportional to the distance squared, the inverse square law. So let's do a little concept check on Coulomb's law. Question is, what is the magnitude of the force F2? If we have two charges right here, and we know that F1 is 3 newtons to the left, is it A, 1 newton? Is it B, 1.5 newtons? Is it C, 2.0 newtons? Is it D, 3.0 newtons? Or is it E, 6.0 newtons? So in this case, we're not given any, distances or any mathematical equations to calculate. This is just a conceptual question. So if this charge feels a force of 3 newtons pushing to the left, then that means F2 will also feel a force of 3 newtons, but in this case pushing to the right, because according to Newton's third law, for every action there's an equal and opposite reaction force. So as hard as one charge pushes on another, the other one pushes back just as much and in the other direction. Next, here's another concept check question to help test your understanding of Coulomb's law. Here we have a system of charges, and the question is, if we increase one of the charges to 4 times its original charge, what would be the new magnitude of the forces acting? So here we have F1 is 3 newtons, and we just figured out that F2 has also got to be 3 newtons. But now we made the first charge 4 times as much charge. Think of it like we put 4 times more magnets there. Would be another analogy there. So what would happen to the new F1, the new forces acting on the charges? Is it A? There would be 3/4 of a newton. Is it B? There would be 3.0 newtons. Is it C? There would be 12 newtons. Is it D? 16 newtons. Or is it E? 48 newtons at work. And the correct answer is going to be C. There will now be 12 newtons of force acting to the left and to the right. So the simple way to think of this is just, there's 4 times more charge here, so there's going to be 4 times more force. So mathematically, this is how you would break it down. The original force, F1, would be K Q1 Q2 over the distance squared. It's 3 newtons. Sometimes instead of D, we'll just use R to represent the radial distance. Next, we're going to have 4 times the original charge. So mathematically, if we substitute that in, then the 4 comes out. So in other words, we have 4 times the original charge, or 12 newtons. So in other words, just using common sense, if you charge something up 4 times as much, you rub a balloon on your head and you build up 4 times as much charge, it's going to have 4 times more electrical force of attraction to other charges there. Finally, we have our last concept check question here to help test your understanding of Coulomb's law. So here we have system of charges, and the force between 2 charges separated by a distance r is F. They each feel certain force here. Next, the charges are pulled apart to a distance of 3r, 3 times further away. What is the force now on each charge? Is it A, 9 times the original force? Is it B, 3 times the original force? Is it C, 1 times the original force, or the same? Is it D, 1/3 the force? Or is it E, 1/9 the original force? And so the correct answer is E, 1/9 the original force. And the way you can think about this conceptually is just, if you move 2 charges further apart, kind of like magnets, they're going to get weaker, the forces. But you have to remember, it's the inverse square law. So if you're 3 times further away, it's going to be not 3 times weaker, but 9 times weaker. So mathematically, the complicated way to look at it is, originally we had a force acting on the charges. So using Coulomb's law, that's K Q1 Q2 over the radius squared there. Next, we're going to have a new force. We'll call that force prime, where now the distance is 3 times further. And notice the 3 gets squared also, so it's 1/9 the original force. So in other words, it's 9 times weaker, 9 times the force as before. So practically speaking, what does this mean? If you're outside and there's a thunderstorm rolling in, and there's a big old thundercloud rolling over your head, and you're in the middle of a golf course, you definitely don't want to be the tallest object. If you can be closer to the ground, if you can crouch down on the ground and you're 3 times shorter than the tallest object, you're not 3 times less likely to be struck, you'd be 9 times less likely to be struck, because there's 9 times less force of electrical attraction between the thunder cloud in your head there.